Hello and welcome to this session. In this video, I'll be talking about forecasting, some ideas about forecasting and tools and techniques that companies can use when they are forecasting. So to start with, just to understand what is forecasting, it's really predicting a future event. In business decisions, typically we are interested in understanding how service or production activities should be planned in the future. How inventories needs to be planned in the future, what should be our personnel hiring and layoff strategy going forward depending on the demand that we might see. If there is facilities that have to be set up, what is the strategy for that, how the demand might shape up. So many of these decisions that we will be taking require us to forecast what we are expecting in the future. Now, forecasting can be divided into different time horizons. The first, at the closest time horizon, we think about it as a short-range forecast. This is up to 1 year, generally less than that, about 3 months. These are the kinds of decisions where what we are doing is more about the next 3 months activities, for example, relating to purchasing of supplies, job scheduling that we have to do over the next 3 months, what kind of workforce levels we want to have for the next 3 months because of current situation of our demand, job assignments that we want to give to people, production levels. These are the kinds of things that we do in a short range forecast. Then comes the medium range forecast, which is 3 months to 3 years, where we are doing sales and operations planning, budgeting. These are relatively longer in time horizon. And then come the long range forecasts that are greater than 3 years, where, for instance, a new service or a new product planning would fall. A new facility location decision has to be taken on a longer horizon. Research and development activities, those kind of decisions will be long range forecasts. Now, when we think about these time horizons, we have to also keep in mind that there are distinct aspects of these time horizons. Medium and long range forecasts typically are looking at more comprehensive, broader issues, and these are the ones that support management decisions regarding planning of products, services, facilities, where real assets may be involved. Big fixed asset investment has to be made. Short-term forecasting usually employs somewhat different methodologies than longer-term forecasting. You do have some data that you can really go into and understand what the patterns look like a little bit more in a fine-grained manner. And typically short-term forecasts are more accurate than longer-term forecasts because it's in the near horizon, time horizon, and therefore we have little better understanding of what might be happening than maybe what will happen 3 years or more than 3 years after where we are at this point in time. So that's why the uncertainty becomes very high when we have a longer term horizon. Now, types of forecasts can also be distinguished. We can think of economic forecasts where we are looking at business cycles, how inflation might play out, what's the money supply looking like, how the housing starts are. Many of the news discussions you will hear really talk about these economic forecasts of what is up there. And oftentimes this is closely related to policy decisions that companies are looking at from the government side. Then technological forecasts. Here we are predicting the rate of technological progress. These are kinds of decisions where we will have to understand, for instance, where is the smartphone industry moving? What is the next thing in the horizon for automotive market? These are technologically changing markets, and many other markets are likewise. In healthcare, you have predictive medicine and a lot of robotics coming into play, and that's going to change the way healthcare is going to be delivered. In manufacturing, likewise, technology, artificial intelligence, Internet of Things, all these things are changing the way products are getting made. Products are getting manufactured as well as developed. So that will have an impact on your forecasts for the future. Then comes demand forecast. These are the ones where we are predicting demand of an existing product that you've already been selling and we have historical data, or existing services that you've been offering. And looking at historical data, we are predicting what could happen in the future. Now, forecasting is extremely important from strategic standpoint, because that's the way we are going to plan going forward. In supply chain management, we could develop good supplier relationships based on our forecast. We can think about the service and product innovation activities we want to involve in. We can also understand the cost and speed to market that we have to keep in mind based on how we think demand will shape up. In human resources, and we can take decisions about hiring, training people, laying off people, depending on how the forecasts are, how the demand might look like. And for capacity, likewise, capacity shortages that we may have in the future, how can we address them? How that can result in some loss of customers, loss of market share. These kinds of questions can be asked based on the forecasting that we have done for the future. Now, a good forecast would have to go through certain steps. There are 7 steps in forecasting. You determine why the forecast is being developed. Select the time horizon to be forecasted. Is it a short-term, long-term, medium-term? Determine the time horizon based on the items that you have. So second is actually select the items that you will be forecasting. You need to know what is the unit of forecasting. Is it the number of units being produced? Is it the number of people that you need for your organization? There could be different items that you're trying to forecast. So you have to determine that as step 2. Third is the time horizon that I mentioned earlier. And then the fourth one is the method that you want to adopt. Now, there are different forecasting methods, and we have to choose the method which is appropriate based on the situation in hand. Then we gather the data that is needed to make the forecast, make that forecast using the data, doing the analysis like we want to based on the forecasting models, and then validate and implement our results. So that's something which we do, and then after we implement these results, we always track how good the forecast is, how much is the error in the forecast compared to the actuals that we're observing. Now, it's a fact that forecasts are never perfect. You will always have error in any forecast you make, because there are many unpredictable factors that will impact forecast. So that is important to keep in mind, and therefore tracking error is essential. Some approaches that companies adopt to reduce the forecasting error include considering the entire product family, because at the family level, when you are forecasting compared to individual products within the family, your forecasts are going to be relatively more accurate. Aggregated forecasts at that product family level are typically more accurate than individual services or individual product level forecasts. So that's important to keep in mind. Now, forecasting techniques, there are several kinds. We can broadly categorize them into qualitative methods and quantitative methods. Qualitative methods are the ones where we adopt these methods when the situation is vague. We don't have too much data that we can rely on. This would be example like a new product has to be launched, and this is a very new technology which does not have a precedence, or a new service that is going to be launched, any new technology that is getting developed. So these are situations where we don't necessarily have a prior understanding of what the market might look like. It involves intuition, it involves experience, so you really try to talk to many experts in that area, and then try to gauge the market that might be there for what you're doing. The other approach is the quantitative methods approach, and there we are employing this method when we think the situation is relatively stable, quote unquote, because nothing is stable. There always can be uncertainties, and we also need to have historical data to do quantitative modeling or forecasting. So these are for existing products. These are for current technologies. Involves mathematical techniques that we will have to use. For example, forecasting demand for X-rays in the radiology department would require us to look at what exactly was the historical demand, and then use that to predict the future. Now, qualitative methods, some examples. One is the jury of executive opinion. So we are taking opinions from high-level experts and then augment it with some statistical models. That way we are kind of bridging uncertainty about what's going to come because of this unknown area that we are delving into, a new product, new technology, but then looking at some statistical models based on what a similar type of product might have done in the past. Or the second is Delphi method, where you're basically considering a panel of experts with different backgrounds potentially, and then you're iteratively querying them about what could happen in the future. So you are trying to kind of gauge a consensus view of what could be happening. Salesforce for composite is another type of qualitative method where estimate from individual salespersons are reviewed for reasonableness, and then they are aggregated across all the salespeople who may have come up with their own idea about what the market might look like, and then market survey, asking the customer what could be what they want and what they think the market might look like if this kind of a product is launched or this kind of service is launched. Now, quantitative methods, if we were to think about those techniques, we can broadly categorize them into those that are time series models. They include naive approach, moving averages, exponential smoothing, and trend projection. And then associative model like linear regression. So we'll take a look at some of these techniques for further illustration of forecasting models. We'll start with time series forecasting, where you need a set of evenly spaced data from the past. Typically, the evenly spaced data is spaced based on time, like every week data you might have, every day's worth of sales you might have, or every month worth of inventory that you've carried in the past might be an example of evenly spaced data that you have. And then forecast is based only on this past value, and you're predicting using this past value. No other information is being used. You're not trying to overlay something else on top of it. When we do time series forecasting, we need to consider different components of the forecast. There's a trend component, there is a seasonality, there is cyclical nature to demand or whatever the aspect that we are trying to forecast, and there's a randomness that we have to keep in mind. So if we were to think of it from a typical graph of demand, this is time on the x-axis, and you have demand for a certain product or service on the y-axis. The demand is sort of, if you can see here, it looks like it's moving upwards. So there's a trend component which shows that it's increasing demand for whatever service this is. There is a seasonality to it, every year, because these are years. Every year, somewhere in the middle of the year, you see the peak happening, and then it comes down towards the end of the year, and then again it peaks towards the middle. So this is a service or product that has a peak somewhere in the middle of the year. So that's the seasonality that you have. Then you have an average demand, which is sort of average across 4 years. What has been the average for this? This fluctuations that you see every year is the randomness that you're seeing. So that's a random variation. On a day-to-day basis, you may have variation, and that is something which is a random component. And if we were to look at it at a very long period of time, not just 4 years, maybe over the course of 25, 30, 40 years, then we might also see some sort of cyclical nature to it. Depending on the macroeconomic environment, maybe there is this service or product that moves in a certain cyclical manner. Every 5 years it goes up and then it comes down, or something on those lines. So we have to keep that also in mind. So there are these types of components within a demand pattern that we can see. These trend components are typically persistent upward or downward fluctuations that we see in the demand. It could be influenced because of changes such as changes in population, change in technology, culture, etc. Seasonal component is essentially up and down fluctuation within a given year. For instance, it could be due to weather, it could be due to customs. A certain months there are certain products that sell more, and it could be just because we have some holiday seasons or other customs that make those products become more popular during certain time. And it typically occurs within a year, right? So that's so for example, in the week, if our period length is week, that's our time unit, then season length could be in days. So within a week, you could expect that towards the middle of the week, something gets sold or services more or something on those lines. Whereas during the end of the week or during weekends, you see lesser service or lesser of the product sales of certain kind. So that's an example of season length being days, and number of seasons in pattern would be 7. We have 7 different days every week. Then you have month within which season length will be week. Every month has about 4 to 4.5 weeks. So therefore, we can see certain in the month, sometimes you could have certain services or products that have fluctuation within a month, and that needs to be captured accordingly. And then we can keep going from there. It could be within month. Sometimes you could have during days, middle of the year, middle of the month, we might see certain services or products being sold more. So that's again possible. And then year and quarter, or year and month, year and week. These are different ways in which period length and season length can be defined, depending on the circumstance that we have in hand. Coming to cyclical component, these are also repeating up and down movement, but these are longer cycles. These are affected by business cycle, political environment, economic factors. So multiple years duration. You have to keep track of data for a longer period of time to understand the cyclical nature. It's often causal or associative relationship. It might be something else is happening, and that's why your demand has this cyclical nature here. And finally, random component is the erratic, unsystematic sort of residual fluctuation that you can see. And these are random variations, unforeseen events, something which we never can predict. This is an error that always will exist in any forecasting model that you will have. And it's non-repetitive, so you don't have a way to capture the patterns that might be there. Now, how do we really take all these into consideration when we are using a forecasting model or developing a forecasting model? Let's take a look at some of the widely used models. The most common, or rather one model which is the most basic type, is the naive approach, which is essentially assuming that demand in the next period is going to be the same as demand in the most recent period. So for instance, January sales were something and we expect February will follow, just like January. Or last year January it was so and so, therefore this year January it has to be so and so. So that's sort of an easy way, a very basic way of forecasting, very cost effective and efficient, good starting point. But obviously not every year January will have exact replica of the previous year. We could be expecting some changes, and that is not being addressed in this approach, and that is the drawback of this technique. The next level of sophistication we can add is what we can call a moving average method. Here we are considering arithmetic means of certain number of periods to predict what could happen in the next period, right? So it's used if there is little or no trend in the data, and used often for smoothing the fluctuation that might be there in the data. So essentially the formula is demand in the previous n periods. You can choose that n period as 2 months, 3 months, 4 months. If it's weeks data that you have, so maybe 2 weeks, last 5 weeks data will predict the 6th week sales or demand. So there is an n that you have to choose, and then based on that you can develop the moving average. So this is an example we have where we have months as our unit, and for each month we have actual sales of a certain product. And we are using 3-month moving average, which means that we are basically averaging every 3 months to find the forecast for the 4th month. So for April, we are taking the average of January, February, and March. And for May, we will be taking the average of February, March, and April, and so forth. Right? So that's something which is sort of a straightforward, simple technique that can be adopted for forecasting. A slightly more sophisticated moving average approach would be to weight the moving average with the most recent data given more weight compared to older data. So this is where we have data where trend exists. You have demand which has trend in it, and we want to capture that trend, and therefore the most recent data becomes more important than the older data, and we want to take that into account. So this weight that we want to associate for every period is based on experience, it's based on intuition. Working in that environment, you get a sense for how much weight you want to give to the most recent month compared to 4 months back. So that's something which is part of this model. Weighted moving average works by taking the weight for a period and multiplying it with the demand in that period and then dividing by the sum of all the weights. So as an example, easiest to understand through this example, again taking the same example, but this time we want to do the weighted average, and we will use these weights. We will consider the most recent month as a weight of 3. 2 months ago it will be a weight of 2, and 3 months ago it's a weight of 1. So total sum of weights is 6. So if I want to forecast for this month, I'll take last month's sales multiplied by 3, the weight of that month. Take 2 months ago sales, what it was, and multiply it with 2, and then 3 months ago what was the sales, and multiply it with 1, and then divide it by the sum of weights, which is 6. So if I apply this approach for this example, for the month of April, I take 10, multiply it with 1 because it's the oldest data. So rather I should start with March because we'll go backwards. 13 is the most recent month's sales, March. So 13 multiplied by 3 plus 12 multiplied by 2 and then 10 multiplied by 1. That's what we did in the numerator. And denominator, we are just adding all of these weights, which is 6. So that turns out to a certain number, which is the weighted moving average forecast for April. And we can do the same thing for rest of the months, and this way we can calculate our 3-month weighted moving average for all of these months that we have here. Now, some problems with the moving average approach is that as we increase n, it smooths the forecast. So instead of 3 months, if I had chosen 4 months or 5 months, it will smooth the overall forecast, but it makes it less sensitive to changes. So if there are changes happening because of certain, something happening within the market, then that is not getting captured as we increase the amount of time that we are using to take the moving average. It does not forecast trends very well, so that's something which is a drawback of this technique and requires extensive historical data. So more the data we have, better we have an idea of what's the moving average time that we want to consider. How long should we be using as part of our number of months or number of weeks that we consider as moving average. So this is a graph that shows you how a moving average and weighted moving average turns out. If this was the actual sales that we are predicting, and if we had chosen the moving average technique, that is this red curve, we'll notice that the red curve is following the actual sales, but it gets delayed a little bit. So it's not, so the peak of the actual sales happened in the month somewhere between July and August, but the peak of the red curve, which is your moving average, happens between September and October, or maybe close to October. So we just miss the peak by a few months because we are doing moving average, and we may not be able to capture it. Weighted moving average at least gets a little bit closer to the time, but still we don't necessarily capture the actual peak when the actual sales were peaking. Even when we use the weighted moving average, we have sort of moved beyond the actual peak, so we could be missing it. So overall patterns look similar, but there is this drawback of first of all missing out on some variations that could be happening, and this delay that could be there. The next method that is very widely used is the exponential smoothing technique. Now, exponential smoothing technique is also a form of weighted moving average, where the weights will decline exponentially with time. As we go backwards in time, the weights are becoming less and less, and that's an exponential decrease that we'll see. So most recent data is actually weighted quite a bit more than the older data. Now, in this approach, you require something called a smoothing constant, which is referred to as alpha. This alpha can range from 0 to 1, and it's subjectively chosen. Right? So this is something which is a value that a company has to come up with based on historically how they've been doing forecasts and what has worked and what has not worked. But there's an alpha that they have to choose, a smoothing constant, because that's coming in the formula. And this approach has the advantage that you don't need too much of data. When you're forecasting using exponential smoothing, you can forecast with relatively less amount of data. So the formula that we use for exponential smoothing is that a new forecast is going to be last period's forecast, what we forecasted in the very recent period, plus the smoothing constant alpha multiplied by last period's actual demand that we have seen now minus last period's forecast. So that's basically the difference between actual demand and forecast. So putting it in the form of a formula, forecast for period t is equal to forecast for period t minus 1 plus the smoothing constant alpha that we have decided within the company multiplied by the difference between what was the actual demand in the previous period minus what was the forecast in the previous period. So this again can be illustrated with an example. Let's take an example here. Let's say our predicted demand was 142 in the most recent period. Actual demand was 153. So we predicted lower than actually what the demand was. Our smoothing constant is 0.20. And we want to know what exactly the forecast should be, new forecast should be for the next period. So for that we use the formula new forecast should be forecast for the previous period, which is 142, plus the smoothing constant, which is 0.20, multiplied by the difference between the actual demand that we saw in the most recent period minus the predicted demand in the most recent period. So that difference multiplied by 0.2. So if we do that, we'll get the new forecast to be 144.2 and approximately 144. So that's sort of an example here. Now smoothing constant we used here, it was 0.2. This smoothing constant can range from 0 to 1 as we saw in the previous slide, but typically it ranges from 0.05 to 0.5. As this alpha increases, what we are doing is older values are becoming less significant. So as we are taking alpha closer to, let's say, 0.5, we are making the older data very less significant. But if we keep alpha close to 0.05, we do want to give quite a bit of importance to older data as well, older values as well, right? So that's something which we can see here. Basically, if I choose alpha as 0.1, the most recent period will get the alpha of 0.1. The period before that will get alpha times 1 minus alpha, which is only 0.098. Then the period before that, it will be alpha times 1 minus alpha squared, which is 0.081. So by the time we come to the fifth period behind, like fifth period, most recent period, then it will be 0.066. And if alpha was higher value, like a 0.5, then you can notice that that fifth most recent period has a lower weight compared to the most recent. So this difference is way more than what the difference between 0.1 and 0.066 was. So that's the key idea here. So here is what happens if you choose different alpha. This is your actual demand. And suppose we used alpha as 0.5. What you can see is that this green line actually captures the fluctuations quite a bit. So it is fluctuating somewhat similar to what the blue line is fluctuating. A smoothing is happening because that's the idea of exponential smoothing, that you do smooth the demand. It is not going to really predict exactly how the actual demand was, but it is capturing these lower ends and the upper ends in certain ways, with some smoothing happening here. But if I was to use alpha as 0.1, that is the red curve, you can see that it's more or less taking an average of the demand for that blue one, and there is none of those peaks and valleys that we saw in the blue line that is getting captured in the red one. So as you increase alpha, you typically will see more of that fluctuation being captured. So choose high values of alpha when underlying average is likely to change, like we have there. And choose low values of alpha when underlying average is stable. If it's a stable demand, then we should choose low values of alpha. Now, choosing alpha, the objective really is to obtain the most accurate forecast, whatever technique it is. Right? So we generally do this by selecting the model that gives us the lowest forecasting error. And that's why every time we are forecasting, we need to understand what the forecasting error is. So if we have chosen a certain alpha, 0.2 or 0.5, we need to account for how much error are we having in our forecast with that alpha, and what would happen if we change that alpha to a different value. So this kind of an assessment has to be there in an organization to understand what might be the right alpha. So it's an iterative process to get to some understanding of what's the right value for alpha. Now these were time series models, and then we also have associative model for forecasting like linear regression, where a dependent variable is related to one or more independent variables. So sales could be dependent on advertising investment that you have made, or R&D investment, or whatever. Some input that you have put into the organization is impacting the outcome variable. So that's causing. So that's why it's somewhat called a causal model, quote unquote causal, because there are other factors also there. So we can never say this is actually causing it, but they're assumed to be caused by some independent variables that have been been accounted for in the past. A simple linear regression model basically is a straight line which has the equation y, which is your dependent variable. Typically it's a sales or demand, equals a constant. We call it the intercept of a line, plus b, which is the slope of the line, multiplied by x, which is your independent variable. So for instance, advertising that you may have done. So that's a typical model for linear regression in forecasting. And if you were to plot it, your demand may have several fluctuations. They're all over the place. So you have independent variable and dependent variable, so sales, and at that same time what exactly your advertising, for instance, was. So there is value all over the place. So what linear regression tries to do is it tries to find that line that passes between these different dots that you may have that relate your independent variable with the dependent variable, right? So essentially the idea is that in the linear regression model, you're trying to reduce this error, on average, the error that is there from that line to each of those points combined. So for all of these points, if I were to take the error from how far they are from the line, and then the sum of squared errors, I'm trying to reduce that, and that would be the line that I'll get to, whichever line results in that lowest error value. So that's the objective here, right? So that's something which we want to do, and typically when we conduct linear regression or do linear regression, we also get to see what's the sample correlation coefficient. It measures the direction and strength of the relationship between independent variable and dependent variable that we are considering. Typically this correlation coefficient ranges from -1 to +1. Some of the independent variables could be negatively impacting sales or demand. Some of them could be positively impacting sales or demand, for instance. So that's an example. And the sample coefficient of determination is something which we also capture in linear regression, which is the square of your correlation coefficient. It basically measures the amount of variation in the dependent variable about its mean that can be explained by the regression line. So if I'm predicting sales as a function of advertising investments that a company has made, that R square is capturing how much of the variation in the sales is being predicted by this one variable, advertising, and the linear line that you have created using linear regression. Again, R square ranges from 0 to 1. A higher value indicates that a larger amount of variation in sales is predicted by this independent variable that we are using. And then there's a standard error of the estimate, which measures how closely the data on the dependent variable cluster around the regression line. If they are too far apart from the linear regression line, then that means there is more standard error that exists. Closer they are, that means we have less of an error. So as an example, just a problem here, let's say a supply chain manager wants to forecast in a better way the demand and believes that the demand is related to advertising expenditures. And these are some sales and advertising values for the past 5 months. We have for every month the sales that we have in thousands of units, and advertising that investment that we have made in the organization, thousands of dollars. So these units are impacted by, say, the thousands of dollars that we are spending in advertising. That's our hypothesis. So the company will spend $1,750 next month on advertising for the product. We want to use linear regression to develop an equation and then forecast how many products will we sell if we were to spend this much next month in advertising. So for that, we can use Microsoft Excel to determine what are the values for the linear regression line AB that we need for the linear regression line, as well as the correlation coefficient, correlation itself, and then the standard error that we want. So if I use Microsoft Excel to just run this particular model, then I will get the intercept as minus 8.135, the slope as 109.229 multiplied by x, because that's what we do in the formula, y is equal to a plus bx. So minus 8.135 plus 109.229 x will be my equation for the linear regression. The correlation coefficient is 0.980, and the coefficient of variation, we are explaining 0.96 of the variation in sales by using advertising as an independent variable and creating a linear regression with it. And the standard error of the estimate is 15.603. So that's something which can be easily captured using Microsoft Excel, and essentially our linear regression equation looks like this. So now if I want to know how much my sales is going to be if I invest, or if I put in $1,750 in advertising, so I replace X with 1,750 and then calculate what the Y will be when I do so. And that will tell me what's the sales going to be for the next month. So this is the approach that we adopt when we are doing a linear regression model. Now, as I had mentioned earlier, for every forecasting technique that we employ, we always want to capture the error that exists. And there are some common measures of error. These include mean absolute deviation, where we take the actual every period, we look at the forecast we had in that period, take the difference of the two, and then the absolute value of that for every single period. And then we sum it. This symbol is the summation symbol. For every period, we just sum the difference between actual and forecast and the absolute value of that. After summing them, we take the average over the entire period. So we're dividing it by the number of periods for which we are looking at the mean absolute deviation. That's one metric that we can use. The second metric is the mean squared error, where forecast error, which is the actual minus forecast, we take the square of that and then add them. So again, summation divided by n, that gives us the mean squared errors. And then mean absolute percentage error, where we take the actual minus forecast like we were doing, but divide it by actual as well for every period. And then multiply it with 100. So we get a percentage error that exists in every period. And then add those all percentages, that's a summation, and then divide by the n, which is number of periods, so that we can get the mean absolute percentage error. So to illustrate this, let's take an example here. Let's say we have the time horizon in quarters. Every year we have these quarter data, and this is the actual tonnage unloaded in a certain organization. We have some value for every quarter that has been available to us, and we are using exponential smoothing technique with alpha 0.1. And we have forecasted these values for every period, while this was the actual, right? So we have actual values and forecasted values for the 8 quarters here. For every quarter, we can, for instance, find absolute percentage error, which is looking at the error that we have in that period. So 180 minus 175 is 5. Divided by the actual, which is 180, so 5 divided by 180, and multiplying by 100 gives us a percentage value. So in that first quarter, we had an error of 2.78%. For the second quarter, we had an error of 7.5 divided by 168. 7.5 is the difference between these two, divided by 168, and that's the actual, multiplied by 100, so 4.46. Like that, we take the percentage error in each of these periods that we have here, sum them, that is 44.75, and then divided by the number of quarters that we have, which is 8. So on average, we have 5.59% error, which is the mean absolute percentage error. So it tells us that this forecasting that we've been doing using alpha equals 0.10 has given us a forecast which has about 5.59% mean absolute percentage error. Now, whether it's a good number or bad number is something which company has to evaluate by understanding what could have happened if alpha was a different number. Instead of 0.1, what if it was 0.18 or 0.2? That's the question that company has to evaluate going forward. Another thing which we can do when we are capturing error in forecast is to look at tracking signals. It's a very interesting metric, because what it does is it indicates whether the forecasting that we are using that has some consistent challenges. It is something where we are trying to understand if we are looking at our forecast, and in that forecast, do we see a consistent overestimation or underestimation in our data, in our forecasts, right? So this is another technique that we can adopt to understand if we have been making forecasts that are consistently biased in some way. So this is useful when forecast systems are computerized, because this way we can alert the analysts when forecasts are really getting far from desirable limits. So we can always set a limit of this tracking signal, and if it goes beyond that limit, then we know that we are, for a period of time, if it goes like that, then we know that we have been overestimating or underestimating our demand. So for each period, we look at the running sum of forecast error. So this should be RSFE, so running sum of forecast error, and that running sum of forecast error is something which then we divide with a mean absolute deviation that we talked about a little while ago. So running sum of forecast error is simply looking at your demand data, whatever the values that you have for every period, and then just adding it with the previous period without taking the absolute value. So for instance, in the first period, if I have a sort of sales value of 10, the next period my sales was 8, and then the period after that it goes back to 12. So each period I have forecasted, instead of 10, I had forecasted, let's say, 8 in the first period. So the difference was 2. The next period I had forecasted, instead of what actually happened, which was 8, I forecasted 9. So I over forecasted. So it was +1. So -2 in the first period, +1 in the second period. So what we will do in running sum of forecast error is we are not going to take the absolute value of this -2 and make it +2. We'll just keep it as -2. For the second period, we'll keep it as +1. And we'll take the running sum of these errors for every period. So first period, it remains what it is, -2. For the second period, it will be -2 + 1, which is -1, and so on and so forth. So every period we do that and then divide it by the mean absolute deviation. And that way we can understand, what the tracking signal looks like. So that will be something which then can be plotted based on what we have maintained as our so-called quote-unquote control limit. Now, this is not the same control limit that we typically use in quality control, but this is a value that we have set as our bandwidth for the tracking signal. And if it goes above or below that, then we have some challenge with the bias that we have in the forecast, and that's what we are trying to track here. So whenever it goes outside that, so you could set it as +4 and -4, or some other value, maybe minus plus. So anything close to 3.75 minus 3.75. These are values that are standardized by many companies as their limits. So every company could decide a certain value based on their product type, the type of forecasting that they are doing. And based on those limits, if it goes outside, that ratio goes outside these control limits, then there is a fair understanding that there is some sort of a bias in their forecast. Either there's over prediction or under prediction that's going on. So this concludes our discussion on forecasting. Thank you.